Okay, so today we are going to study something with a more topological flavor to it. Uh, that is index theory and limit cycles. Of course, I don't think we'll be able to get to limit cycles in this lecture, but let's see. So I'll just name it as part 1. So index theory is very analogous to, if you look at it, Gauss's law has the same sort of a flavor. Uh, it's one thing to have a knowledge of the electric field by using the Coulomb's law. One is other way of determining the electric field is using the Gauss's law, which relates the flux to the net charge enclosed within a surface, a given surface. So this had more of a local flavor to it. You take each point charge, you calculate the electric field. So this is a distribution of charges. You calculate the electric field due to all of these, and you use superposition principle to add them up. Gauss's law takes into account some sort of a spherical symmetry, of course, or other kind of cylindrical symmetry or azimuthal symmetry, and it gives you, in some sense, global information about the flux of a field, flux of a vector field, of the flux of a vector field. Similarly, in the theory of dynamical systems, we have extensively done linearization. It was a local method to determine, looks at the neighborhood of the fixed point of a given, usually we do it at fixed points, but that's not necessary, fixed point. And index theory gives us, so this was linearization. On the other hand, we have index theory, which gives global information about the phase portraits, vector fields, so on and so forth. So let's see what, so in that sense, index theory is topological in nature. By topological, I mean that we are not actually interested in very precise calculations. What's the eigenvalue of a fixed point, or we had this sort of a diagram with the product of eigenvalues, sum of eigenvalues. Here we are actually concerned about the property of the vector field in a phase plane, or in any phase space generically. And the way we do it is the following. So first of all, why this is topological is that index theory is intimately related to what we call as the index of a closed curve. So we'll be dealing with simple closed curves. For example, this is a simple closed curve. This is a closed curve, this is not a simple closed curve. And by the way, when we deal with simple closed curves, these could be trajectories, but not necessarily. So it is not that I am following one trajectory in the closed curve. That is certainly one of the examples. That this can be in general any closed curve, uh, and the vector field might point in different directions or so on and so forth. This could be a trajectory, but not necessarily. So in that sense, this is more like a Gaussian surface. The electric vectors might be piercing it. The only requirement I have is that the closed curve should not pass through a fixed point. Okay, so having set up the rules of the game, what sort of a closed curve we are looking at. Let's see. So what exactly is an index? Say this is a closed curve and I have a vector field pointing towards this direction. So I have some x dot y dot pointing towards this direction, and I am interested in this angle L, theta. How this theta is changing as I am going around this closed curve. So for example, my vector field changes, so my theta angle is changing. Vector field changes, my theta angle is changing, and I am interested in the net change in this angle as I start from a particular point, go around closed curve, and then come back to the same point, theta. So as we go around this curve, the vector field changes directions. One can keep a track of how many revolutions the vector field takes. So as the vector field x goes around the curve C, so this is the curve C, and by convention I am going to go around the curve in the counterclockwise direction. Once counterclockwise, then the angle phi or theta, whatever you might call it, so I'll just call it phi because I have phi in my notes, doesn't matter. Then the angle phi changes continuously if x dot y dot are continuous functions of x. So if my field is well behaved, it's a continuous function of f, then of course as I go slowly around this curve, my angle is going to change very slowly and continuously, are continuous functions of x. So I denote that change around the closed curve by this square brackets. This represents the curve I'm on in the counterclockwise direction. It's always going to be the counterclockwise direction, so this is redundant. So this is the net change in the angle phi as one goes around the curve, and of course reach the place where I started. So you can imagine, essentially you have a vector field and like your pen, and as so for example this vector field, nothing happens. You go around this curve and you come back, your vector field doesn't change at all. Imagine your pen aligned with the vector field, and as you go, nothing is happening to your pen. It's the same thing. The compass remains the same. So over here, phi c is 0. Or in other words, so I define the index IC, index of a curve in the vector field, as something like 1 over 2 pi, this guy, just the angle 2 pi divided by the net change. So this is denoted as the index of the vector field. And you also note that the angle, the net change angle, is always going to be a 2 pi, or shall I say a multiple of 2 pi and why is that so? Can you tell me why? See, if I am starting from here where the vector points here, no matter what I do, I come back to the same point where the arrow is pointing to the same direction. I come to the same point. So either it has to be a 0 net rotation, it has to be a 2 pi net rotation, or it has to be a zoom 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 4 pi net rotation of this arrow or the vector field. So always it's going to be a multiple of 2 pi. So this is called as the index of the vector field, or index of the, I should say, curve. See, with respect to the vector field. So we already did the example where the index was, in this case the index was 0. What happens to, let's say, a vector field which is radial all the time? See, here the angle is 90, is changing. It's now this angle, the entire angle. So here the index is plus 1, because as I loop around the curve, the vector field completes 1 2 pi rotation. So the net change in the angle is 2 pi. So you might be in your mind saying that this is more like the curl of the vector field, which also captures some sort of a rotation. But remember, the curl is defined at a point, whereas the index is defined along the curve. So, for example, imagine a vector field. Once again, this guy, 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 something like that. This guy, and I have the other directions, something like that. So what's happening? I start here and I am actually going counterclockwise, but now my rotation angle is minus theta, minus 90 degrees, so on and so forth. So over here, when I close the loop and come back again, I'll have a net motion of minus 2 pi. So over here my index is negative 1. So this is how I define the index of a curve with respect to a vector field, and this is a very elegant concept in dynamical systems, and it tells us sometimes a lot of information about. So because dynamical system essentially is a vector field, the way we have defined with x dot and y dot at every point. So this is a vector field, and the index is telling you something about a region of the phase space with respect to that vector field, what's happening in that region. So we'll go to the properties of the index. So what happens if the closed curve is itself a trajectory? So now it need not be, but let's say I have a closed curve in the phase space and that is my trajectory. So this is also a trajectory. So in this case, you can imagine, right? I'm here, then I'm here. Each time I'm aligned, and by the time I complete the curve, my net change of the angle is 2 pi, and the index is 1. One more property is that index is additive. If we subdivide the curve. So for example, let's say I have a curve which I divide it into this way, C1, C2, or C1, C2, let me call it this way. So I'm going around this curve, which was subdivided into two curves, C1, where I go around this way, come this way, and go around this way, come this way. So C is comprising of C1 plus C2. because these two paths cancel each other. And the property of the index is that the index of the curve C in the same vector field is IC1 plus IC2. And it's more like, so this index is very similar to when we do complex analysis and contour integration, the formula by Cauchy and all. But you can easily see why. So, see why this is true. The proof is essentially that these two paths, like the one vertical and these two paths undo each other when we add IC1 and IC2. So contributions to the change in the angle phi on the bridge, I'll call this as a bridge, this guy, or two parts, on the bridge cancels on C1 and C2. If I'm going along this path, I see the vector field and the change in one direction. If I'm going along the entirely opposite path, it cancels out. My change in angles are in the opposite direction. So this holds because this guy. Okay, so that was good. What is the third property of the theory of indices? If I deform C continuously into a new curve, C prime, without passing through a fixed point, then the index does not change. So I'll just write it down. If I deform C continuously into a new curve C prime without passing through a fixed point, then the index does not change. So IC is IC prime. So this is kind of like the Gauss's law, if you can look at it. As long as you deform the surface and it doesn't, so this is deformation, this is Gauss's law. As long as the net charge enclosed is the same, you don't change the flux. No change in the flux. Similarly, as long as on the curve you are not passing through a fixed point, these things remain the same. So what's the proof? Well, the proof is rather simple. I have C prime, and I am deforming IC is being deformed uh, continuously to C prime, and by the continuity of the vector field, these vector fields, if I am deforming them continuously, these vector fields change by very little, uh, and what I mean to say is that IC, the index depends continuously on C, but IC is an integer. IC is an integer. Remember, that is because the change of angle is always a multiple of 2 pi, some multiple of 2 pi. So something which depends continuously on a curve which is being continuously deformed, and something that is an integer, the only way to reconcile with these two things is that it has to be a constant. So continuous function that is integer valued has to be a constant. So therefore IC is equals to IC prime. And of course this holds when see, we are not talking about, remember we ruled out the case where my continuous curve was passing through a fixed point. So let's say this is a fixed point. A fixed point is a position where x dot y dot is 0, and the direction of a 0 vector is ill-defined. So phi is ill-defined for a 0 vector. Okay, so the fourth property of the index, coming from the previous third point, I am continuously deforming it. So I can say that if C does not enclose a fixed point, what do you think the IC should be? So I have a curve, I have a phase portrait, and I have a curve here, I have a vector field, and this region has no fixed point. No fixed point. So in that case, IC is 0. And the easy way to see is that you continuously deform this surface smaller and 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 smaller till you reach a very, very, very small region. And on a tiny closed curve, hello? Yes, yes, please speak fast. Okay, okay, okay. Sorry, I got a phone call. Yeah. So, uh, yeah. So I can keep shrinking down, and on this almost to a single point. So keep shrinking perturbatively to a single point. On a tiny closed curve, vectors point more or less in the same direction. I am vectors point more or less in the same direction, and hence the index is 0. Remember, the vectors on the tiny closed curve, for the index to be +1 or -1, they should at least cover 2 pi. But on a very tiny curve, they more or less point in the same direction, and hence IC is 0. IC has to be an integer. Okay, now something interesting. So what happens, do you think, when I make time negative? So x dot, y dot, they would probably go to -x dot, -y dot, or in other words, the vector field completely reverses its sign. So what does that mean? That means that each point of the vector field is rotated by 180 degrees. So phi goes to phi plus pi. But the net change in phi is 0. It is just that at each point of the vector field, now I am dealing with this vector. This vector, this vector, this vector, as opposed to the original field vectors, this guy, as I am traversing this path. But notice, I am basically interested in the change in phi. So the net change in phi doesn't matter, these guys. Now I am interested in the change of these guys rather than these guys, and that change is the same. So nothing happens. So the bottom line is that, and what happens when I rotate a vector field, or each point in the vector field is rotated? Well, one of the consequences, the dynamical consequences, is that the attracting points become repelling points, and vice versa. So if I have a point, that will become an unstable node. So that gives us the following information. Index is not related to stability. So these two have the same index. So index is not related to stability. However, index has something to do about fixed points within a curve. Index has something to do with the fixed points within a curve. So with all that thing, we can also define an index of a point. So index of a point, essentially index of a point is any closed curve that includes that point. Any closed curve that includes that point. And by the way, only that point. So index of a point P is the index for any curve C that encloses P and no other fixed point. If you include other points on the face space which are not fixed points, that's not going to change your index. No other fixed points. So you have any point, need not be a fixed point, that can be indexed as long as there is no other fixed point. You can keep shrinking this curve down to this point. It can be a fixed point, it cannot be a fixed point, but at the end of the day, it should only, if P is a fixed point, it should, or index of P is the index of all these guys, as long as this entire plane doesn't, entire region doesn't contain any other fixed point. It is only when you include these fixed points, your index is going to change. So, of course, by 3, since we ever had the permission of continuously deforming the curve, this notion is well defined. Okay, so we can do a few examples. So for example, if I have a node, we've already seen the index of the node or the point was, see now from talking about index of a curve with respect to a vector field, we have switched our lingo a bit and we are defining index of a point, because that essentially means index of any curve that encloses that particular point and no other fixed point, sort of. So this is also much like the Gauss's law. As long as you are deforming surfaces by not encompassing any other closed charges, sources or sinks, then this sort of a definition holds. So index of a node is 1, and it doesn't matter whether it's unstable or stable. Unstable or stable, as we have already seen. What about the index of a saddle? So I have some sort of a saddle. I have one unstable direction and one stable direction, and if you calculate it, the index comes out to be -1. Similarly, you can show that the index of the spiral is also +1. Doesn't matter if it's a stable spiral or unstable spiral, it just depends upon the type of the fixed point rather than its stability, so to speak. And index of a center is also +1. And of course, index of an ordinary point, as we have seen, is 0. So that essentially is, if I have to draw the face portrait of these guys. So we have tau, delta, our familiar thing, and essentially what's happening is that over here on this plane I have the index as +1, and here I have the index as -1. And you can see why. This represents, this foot represents my nodes and spirals, centers would lie along this line. So as long as this guy, the determinant is greater than 0, So determinant greater than 0 means that either I have both the eigenvalues positive or both eigenvalues are going to be negative. So, and over here are my saddle points where I had one eigenvalue positive and one eigenvalue negative. And the index is not defined upon, not well defined. On non-isolated fixed points. And why? That's because we can't draw curves that close without intersecting fixed points. Remember, one of the ways we defined a closed curve was that it should not pass a fixed point because the angle phi is not well defined on the fixed point. So that was our lecture on index theory. We'll see some interesting theorems soon. Thank you.